Your hardware wallet is sitting in a safe, unplugged, completely offline. Yet right now, your phone can generate a brand new Bitcoin address for an incoming payment, and that hardware device will know how to sign for it later. How does one device create addresses that a different disconnected device can spend? Start with the core identity of elliptic curve cryptography. A private key, lowercase k, is just a large random number. The public key, capital K, is that scalar multiplied by a fixed curve point called the generator, capital G. So K equals K times G. Scalar multiplication on an elliptic curve is easy one way and practically impossible to reverse. Given K, nobody can recover K. That one-way relationship is what secures every Bitcoin key pair. Here's the trick. Elliptic curve points can be added together and the scalar multiplication distributes over scalar addition. That gives us this identity. Capital K plus T times capital G equals the quantity lowercase k plus T times capital G. We'll call T the tweak. On the left side, we take the public key capital K and add the point T times capital G to it. That uses only public information. On the right side, we add T to the private key lowercase k, then multiply by capital G. Both paths land on exactly the same point, the child public key, capital K prime. Same destination, two different routes. One requires the secret, the other doesn't. Let's make this concrete. Pick a tweak equal to 123. First, compute 123 times G, the public curve generator point. Add that result to the public key K, you get a new public key K prime. Now separately, take the private key little k, add the number 123 to it, and multiply the sum by G. You land on the exact same K prime because K prime equals K prime times G, where K prime is simply K plus 123. This is a valid key pair. A real private key secures a real public key. We just generated a child key pair using only addition. Let's run the scenario with two people. Alice holds both the private key little k and the public key big K. She sends big K to Bob, keeping little k secret. Now Bob wants a fresh public key for a payment. He picks a tweak, say 123, and computes big K plus 123 times G, getting big K prime. Bob then sends the number 123 back to Alice. Alice computes little k plus 123, and now she owns little k prime, the matching private key. Notice that the tweak itself is not a secret, it's just a recipe. The security lies entirely in Alice keeping little k private, and if tweaks are generated deterministically, say by hashing a counter, anyone with big K can produce an unlimited sequence of child public keys without any back and forth at all. Map this onto real hardware. The hardware signer, often misnamed the hardware wallet, holds the master private key in cold storage. It never touches the internet. On the web front and running on your laptop or phone, holds only the master public key K. When a customer wants to pay you, the front end picks a fresh tweak, computes a child public key, and shows the address as a QR code. It can do this thousands of times without ever contacting the hardware. When you decide to spend, the front end builds an unsigned transaction and hands the tweak path to the hardware signer, and the signer derives the matching child private key on demand signs and returns the signed transaction. The private key never leaves the device. The front end never sees a secret. Both sides agree on the same key pair through pure algebra. One nuance worth flagging. In the scheme we just described, if an attacker learns a child private key, K prime, and also learns the tweak T, they can simply compute K equals K prime minus T and instantly recover the master private key. That's the downside of this shared tweak derivation, which is called non-hardened. For sensitive branches, BIP32 defines a hardened variant. Instead of using a public tweak, it mixes the parent private key itself into the tweak through a hash, roughly hash of K concatenated with the index. Hardened derivation deliberately breaks the public side trick, so you can no longer derive child public keys from the parent public key alone. The payoff is isolation. A leaked child key reveals nothing about the parent. And the rule of thumb is simple. Use non-hardened where you need watch-only capability, and use hardened where you need isolation between branches. Now scale this up, not one child, but a whole tree. BF32 takes the twig trick and applies it recursively. Each node in the tree has its own key pair and its own chain code, a secret that deterministically generates twigs for its children. Start at a master key, derive account 0, account 1, a payroll branch, a treasury branch. Under each account, derive a receiving chain and a change chain. Under each chain, derive individual address keys, thousands of them, indexed 0, 1, 2, and so on. Every path, every branch, every leaf, all reproducible from the same 12 or 24 word seed. One backup protects the entire tree forever. The corporate accountant and the teenager with a browser extension are both running the exact same algorithm, just with different branches mapped to different purposes. Step back and see what one algebraic identity brought us. Because capital K equals little k times capital G is linear, adding the same twig to both sides preserves the relationship. That single property enables watch-only wallets that generate fresh addresses without ever touching a secret. It enables hardware signers that stay offline forever, while online software handles customer-facing flows. It enables exchanges to assign a unique deposit address to every user from one master key. It enables multi-sig coordinators to synchronize key derivation across multiple parties. It enables the 12-word seed phrase that backs up a lifetime of addresses on a piece of paper. Every modern Bitcoin wallet, hot, cold, hardware, mobile, multi-sig, is built on this trick. One line of algebra, capital K plus T times capital G equals the quantity little k plus T times capital G, underpins the entire user experience of self-custody. The linearity of elliptic curves is doing the heavy lifting every time you generate a new address. That's the math making hardware wallets work.